Okay, this is 29.2 electronic devices. We're going to talk about diodes and transistors, talk about light emitting diodes, and how the current actually moves through those things, and then how they make a microchip. So first of all, diodes. They're made of two layers, right? Diode, meaning two. And it's P-type or N-type semiconductors. Remember that the P-type is the positive one. It has a hole. It's missing an electron. And the N-type is negative, so it has an extra electron. It's a donor. So the free electrons on the N side, your extra electrons, naturally want to move into the positive holes. They're attracted that way. And this causes the N side to move easily into the P side. Now, depending on the orientation of the diode in the circuit, that will either make it a very low resistor, since it naturally wants to do this, or if you turn it around, it makes it a high resistor for a little bit and then a low resistor. Okay, so let's talk about different orientations of these diodes. Let's say we have a circuit, and usually these circuits have resistors in it, but we'll just simplify it for now. Here's your diode. Doesn't matter what it is. This is the positive side of the battery, and this is the negative side of the battery. So think about your electrons. If you have electrons and current goes in the opposite direction in which the electrons are actually flowing, so your electrons are going around this direction. So if they hit this side, and this is the N side, and this is the P side, these electrons are going to come over here and go boom, and then zip right over into these holes. So this is called a forward bias diode, because it's in the proper orientation for this circuit. And it has a very low resistance, because the electrons naturally flow to the positive side of the terminal. So that's forward bias. The other one is called reverse bias. And that's where you put it in the opposite direction. So the electrons flow along here, but these are the holes. So they fill up the holes first. And once the holes are filled, so that's a very high resistance, once the holes are filled, then it will move over to the N side and kind of push its way through. So this is reverse bias. And it's a high resistance until those holes get filled, and then it's a low resistance. right, here are the equations that go along with these diodes. We have the voltage of the battery, so VB is equal to the current and the resistance of the circuit. So most of these will have a resistor in here that is either before or after, usually before, the diode to control what's going into the diode. So this is of the circuit. And then we have the voltage on the diode. Now remember that V is also equal to IR, so if you have the I of the diode or the R of the diode, you can break it down a little bit more, but usually VD is all you need. And if you happen to have more than one diode, let's say we have a whole bunch of these in series, remember that voltage is added. So all you have to do is add the second diode on there. So it would just be IR plus the diode of the first one and the diode of the second one. If you had more in series, you just keep adding on to the end.
What does the B stand for?
Battery.
Battery?
Mm-hmm. All right, let's talk about light-emitting diodes. You've probably seen these, LEDs, right? Light-emitting diodes are either made of aluminum, arsenic, or phosphorus. They're made of all three of those things to emit light. Now, what happens is it's used in the forward biased direction, so the electrons naturally want to go from the N side to the P side, but because the materials are such low resistance, the electrons, they pretty much zip right across to the P side with so much energy that they end up in the higher electron level, energy level. So when they drop down, they emit a photon. So it's forward bias. Electrons have so much energy that they emit a photon. Someone was asking a question about LEDs earlier. I can't remember what it was, but because the electrons are just emitting photons because they're in a higher level, there's not a lot of wasted energy, so you don't get heat because all that energy goes straight into the photon. So that's why compared to the normal incandescent bulbs, the LEDs don't give off a lot of heat. For an incandescent bulb, what they actually do is the filament heats up so much that it emits light, so there's a lot of extra energy wasted, and that's why LEDs are considered more energy efficient, because most of its energy is converted into light instead of into heat.
Is this only in the forward direction, not the reverse?
In the reverse direction, I don't think that it could happen because, remember, the electrons have to build up on this side and then move over, so they don't want to go this direction. So I don't think that they'd end up with enough energy to do that. All right, transistors are a sandwich of material. They end up with the P-type semiconductor, then the N, and then the P, or the NPN. So you have PNP transistors or NPN transistors. Now, transistors, since there are 3 layers, they have to go through the doping process 3 times to make the sandwich. And the PNP transistor amplifies small voltages. So let's say you have a 9-volt battery and it needs to be like 12 or something like that. You would put it into the circuit, and it's going to amplify its voltage, just like the transformer did for alternating current. So the transformer, alternating current, it transforms its voltage. The transistor is direct current, so this is used on your microchips, right? You can't use a transformer on your microchips because a transformer needs alternating current, which has changing magnetic fields. Direct current does not. It's a nice direct single thing. It doesn't have the changing magnetic fields, changing electric fields, so we can't do any of this stuff. So we have to have some other object that will transform voltages, and that happens to be the transistor here. Now, since it's used to amplify small voltages, that means if the voltage goes up, current goes down, because we can't violate the law of conservation of energy. So the transistor just changes the voltage, and then it'll drop the current in order to do that. So that its power, its energy stays the same. Now, if you turn it around and you have a different transistor, the NPN, this will make the voltages smaller. So the positive one, the positives on the outside, makes voltages higher, and NPN makes voltages smaller, which means that it's going to increase its current. Okay, for transistors, we have a couple equations. Our transistor equations talks about current ratio. So we have current gain. I gain is the current collected over the base current. And in your problems, it'll tell you collected, base, or gain. And then the current emitted is just the current base plus the current collected. So you have one that's a ratio and one that's just an addition. All right, microchips. Microchips start with a silicon crystal, which I'm from the Northwest, where there's a bunch of Intel labs and stuff. So there's like this little Intel Learning Center that we always went to every couple of years. I think I went once in 6th grade and once in high school or something. And they grow, and I got to see one of these silicon crystals. They grow these silicon crystals, and they actually look like this. It's kind of neat. Silicon cylinder. And they cut them into wafers. So you have these nice circular wafers. And then they print the processors on there. And I think they said something like one silicon wafer makes like 125 processors or something like that. So they have these little tiny processors. Now, they make the processors by doping, right? You remember what a dopant is, adding on materials to make the diodes, the resistors, and the transistors. So a resistor is one layer of this semiconducting material. A diode is 2 layers of the material, and a transistor is 3 layers. So they take the wafer and they put on like a coating. Think of it as like just a plastic screen or a plastic coating, and it has these little tiny holes in it. Then they stick the wafer with the coating on top of it into a vacuum chamber and vaporize the dopants. And the vapor condenses onto the protective coating, and then they take it out and they pull the protective coating off. So everywhere there was a hole, now there's a dopant. So then they put a new protective layer on there with a different set of holes, put it back in the chamber, and add the next layer of dopants. Take it out, pull the wafer off. So now you can think of it as printing little tiny diodes and transistors on there. So to have a diode, it needs to go through the process twice at least. And then for the next one, for a transistor, you have to go through at least 3 times. So that you end up with layers of transistors and diodes. I thought that was cool. All right, I think I have 6 clicker questions for you today. Here is the first one. What does a forward biased diode do?